Now we want to explain why regular submanifolds are the same as embedded submanifolds. Recall that we define an embedded submanifold as a map from a manifold, right, into M, a map such that that is a homeomorphism onto its image, where its image is equipped with a subspace topology, and it should also be an immersion, so that means that it's injective on tangent space. Now, or alternatively, some people define an embedded submanifold to be this image instead of the map. Now, if we have a regular submanifold, i.e. it's a subset of M that is a topological subspace of M that is locally cut out by coordinate functions, then we can view it as an embedded submanifold in the following way. So obviously the map we should look at is the injection. Now obviously this is a homeomorphism onto its image because that's just the identity map. So we want to show that this is an immersion, but that's also clear that it is a smooth immersion, because to check that we just need to check it on local coordinates. And remember, we can choose x1 xr, this first coordinate, to be a local coordinate on n, right? And the map I here, it's just going to correspond to this injection into M. And clearly this is a smooth map and it's injective on tangent space. So a regular submanifold is an embedded submanifold. Now we want to show that an embedded submanifold is also a regular submanifold. In other words, we actually want to show this image, the image of a manifold N under such a map F as described here must be a regular submanifold of M. To this end, we want to use a general theorem called the constant rank theorem, or it's sometimes just called the rank theorem. This is a generalization of the inverse function theorem. Let's say we have a map F, a smooth map F between smooth manifold, and this map has constant rank R. Then we claim that there must exist coordinate charts on M and N. So at every point P, there must exist coordinate charts on M, center at P, and on N, center at FP, such that with respect to those charts, F is going to be given by the following formula. So in the specific case for example, if F is a submersion, that means that it's surjective, right, on tangent space, then this will just correspond to the projection map. Note that in that case, the rank must be N. And if F is an immersion, then the rank must be M. F is injective on tangent space, and the map by this theorem will be of this form. So it is this case, when F is an immersion, that we want to use to prove that a regular, an embedded submanifold is a regular submanifold. Now, because F is an immersion, by the constant rank theorem, we know that there must, for every point P, there must exist some chart center at P, and some chart in M center at FP, such that in these coordinates, F is given by x1, xn mapping to this. When you look at this, you might say, oh, doesn't this already prove that Fn is a regular submanifold? Isn't Fn locally cut out by coordinate function, in particular right here? Isn't Fn intersect with V just the zero set of these coordinate functions, these ones? Well, not quite. We didn't actually prove this. We never proved that this actually equal. What we proved is that f of u is gonna be cut out by this, but Fn intersect with V though might be bigger than Fu. As an example, let's look at the inclusion of the interval -1, 1 inside the plane, the xy plane. Let's say we want to show that this is a regular submanifold, so it's cut out by some coordinate function. Let's call the coordinates on the plane x and y. Then if we use this chart, this open set with the same coordinate function, then indeed this interval is just going to be cut out by y equals to 0. That's good. However, on the other hand, if we use the following chart, so same coordinate x and y, but we use a different domain, then this interval is no longer cut out by y equals to 0, because y equals to 0 on this chart is this full interval, right? And so what we need to do is to shrink the domain of this chart. Okay, so that's what we will do with V. Now the idea here is that the map F was supposed to be a homeomorphism, right, into its image, and this image here has subspace topology. So that means U here, if U here is open, then FU is open in Fn, and because that's in subspace topology, that means that Fu must be the intersection of Fn with some open set of M, V prime. Then if we just shrink V to V intersect with V prime, then we actually get Fu. So on the coordinate neighborhood V intersect with V prime, then indeed Fn is going to be cut out by these coordinate functions, and this shows that an embedded submanifold must be regular. So we can think of these two concepts interchangeably.